Hi guys, and welcome to today's lesson on gradient of a straight line. Yes, I know you're sitting there going, hold on a moment, is this year 8 maths? And I'm going to say to you, no, but it is certainly revision, and it's part of the Methods 1 and 2 course. If you're over here in Australia, welcome. If you are all over the world, welcome. Please don't switch off. This is a great video on gradient of a straight line. It's going to tell you everything you need to know, not only for this course, but for the future. Now, if you're new to my channel, hi, welcome, thank you. I'm Darren, MaffsGuru. Really good to see you. Can you do me a favor? There's a red arrow over there pointing to a little doohickey for YouTube that I would be deeply, deeply grateful if you would subscribe. Subscribers make all of the difference, and this little person who's trying to do a big job would be greatly, greatly appreciative. Otherwise, look, if you're not sure about it, leave it. There's a chance at the end of the video as well. Now, what am I going to do? I'm going to show you about gradient of a straight line. But I'm going to do more than y equals mx plus c. I promise you that. I'm actually going to relate it to methods 3 and 4, parts of the unit at the end, and curves and all sorts of stuff. So what I'm going to teach you is a little bit more than just equation of a straight line. So as I say here, by the end of the lesson, I want you to be able to know what the gradient refers to. Know that gradients can be positive, they can be negative, they can be flat, they can be vertical or infinite or undefined. Know how to find the gradient of a straight line. Yep, I know, I'm really sorry. Just dropped off for a moment. And know the relationship between the gradient and the size of the angle of elevation. Now, what I mean by that is, there's the x-axis, there is our straight line. Can we find this angle here? And believe it or not, you already know the theory. We did it in year 9. We just didn't tell you. We just didn't. Yeah. Now, actually, this lesson is a continuation on a series of videos on coordinate geometry and linear equations. And the previous video is showing above me now for you to click on if and when you want to. But let me just say now, when I said a moment ago I'm going to fast forward, I literally meant that. Why on earth would we need to know about the gradients of straight lines? Well, here is a curve. If I asked you to find the gradient at that point there, what would you do? Well, you wouldn't, because I don't think we've ever actually shown you how to find the gradient of anything other than a straight line. When I was at school, we had to bring out a ruler, we'd put it on the curve, and we'd sort of make sure that it's sort of straight, we'd draw a line, and then we would use that whole rise over run rubbish. And obviously, as you can tell, is that going to give you an accurate gradient? No. But there is a subject coming up called calculus, more specifically differentiation, that gives us a really easy mathematical tool to find the value of the gradient at any point on a curve. Now, obviously, I asked for that point there, but what about the gradient here? And what about the gradient here? Well, hopefully you already know that, because the gradient of a straight line or a horizontal line should be 0. And what do you notice about each of the points I've highlighted? They are maximums and minimums of curves. Now, way back in, I don't know, year 10, you were drawing parabolas, you were maybe drawing cubics, and we were probably telling you, you can't find the values of the turning points. There's no mathematical way to do it, so just leave them, draw a sketch. Well, actually, there is a way of doing it, and as it turns out, that gradient there of 0 happens every time there's a turning point, and we can use differentiation to help us find the actual coordinates. So that's what we're fast forwarding to, but sadly, yeah, I'm really sorry. Finding the gradient is, this particular chapter is just finding the gradients of straight lines and what have you. So basically, there is a line segment between 2 points, and how do I find the gradient? Yes, you're screaming at me now. It's rise over run, and absolutely it is. So there we go. There is my right angle triangle, which I'm very keen to draw. And so now I can find my rise over my run just by counting squares or looking at coordinates. So I have -2, 2, and I have 2, 5. So my gradient, which in maths methods is given by M and all the way back down. I don't know why. Barry has been at it again. I mean, let's choose a letter for gradient. Barry, what do you reckon? G? No, G's already gone for gradient, for gravity. Oh, what letter do you want to choose? Oh, I don't know. M? Yeah, that's good. No one will remember that. M gradient. Why would they? So the gradient is equal to rise over run. And obviously, in this situation, you always have to make sure that you do the y coordinates first. Now, how do we do that? We look at the difference between 2 and 5, and so my rise in that situation is 3 units, and my difference between a run is -2 to 2, which is 4 units, and the world goes crazy, and half my audience is now switched off going, really? 5 minutes, and you've taught me nothing. That's not true. I taught you about differentiation. Come on, give me a break. So there's my gradient, rise over run. Now in that situation, we have a positive gradient. It's sloping up. What would happen if I had a negative gradient? Well, believe it or not, that value would be -3 over 4 for obviously different points. But the principle is really, really simple. So here we go. There we go. We've got formally that the gradient from earlier years is rise over run. We now know that gradient here can be expressed using the letter m, which will come back to y equals mx plus c in a moment. But of course, in methods, Barry's at it again. Why on earth would we want you just to remember rise over run when we can throw letters into it and confuse the bejeebus out of us? So here we go, ladies and gentlemen. Another way of expressing gradient is equal to y2 minus y1 over x2 minus x1. Now, I'm going to oversimplify this, and again, you're going to scream at the screen, going, what are you doing? We know this. I know you know this. It's all right. There will be about 8 people who are watching this who don't know this, and I want to make sure that they do understand what I'm showing. So here's my right angle triangle. Now, obviously, we've been dealing with a coordinate here and a coordinate here. And once we know those two coordinates, we can work out our rise, we can work out our run. For a generic coordinate, we could label this as x comma y, and we know that that could be x comma y as well. But mathematics suggests that when you label x as a value in a question, it has to say the same value all the way through. And we can blatantly see that that value there and that value there are not the same. They can't be the same because they're not the same coordinate. So we add a little subscript, those little numbers underneath there are called subscripts, to stand for our two different coordinates. So what is my rise? My rise is my difference in height. So we know my second coordinate has y2, my first coordinate has y1, so that becomes y2 minus y1. And in the same way, we take the bigger x value away from the smaller x value, which would give me x2 minus x1, and bearing in mind this, here is my rise. And bearing in mind this here is my run. Life is good and we is done. Now, there we go. That's why we do y2 minus y1 over x2 minus x1, which is just more formally saying rise over run. Find the gradient between those 2 points. These are the type of questions coming up in a textbook. I know, seriously, this is it. Find the gradient between those 2 points. So using the formula, I'm going to do m is equal to y2 minus y1 over x2 minus x1. Well, I suppose the question now is which gradient, which of those equations is x1, y1, and which one is x2, y2? Well, it doesn't matter so long as you're consistent. So I'm going to say that that's x1, y1, and I'm going to say that that's x2, y2. Now, notice the way I write that above. It's not because I'm special. It's not because I need to do this. It's just because it helps me visually make sure I put the right numbers in the right place. So y2 is 2, minus y1 is 5, and x2 is negative 2 over x1 is 2. So y2 minus y1. So substituting in the values, 2 minus 5 is, minus 3. Hold on a moment, I was expecting 3. Oh, minus 2 is minus 4. And the minus unter minus gives me the plus. And there we go, 3 on 4. I know, it does actually come in handy in the next video, but then we move on to the very exciting idea of gradients of horizontal and vertical lines. We've already said that for differentiation, gradients of horizontal lines are 0. We already know that. If you're on a bike trying to go up a hill, the chances are you'd prefer a flat hill, in which case it wouldn't be a hill. But that's a whole new discussion. So horizontal lines have a gradient equal to 0. Why? Well, if we look at rise over run, okay, what rise does this thing have? If it's a horizontal line, does it go up at any point? No. So my rise is 0. It doesn't matter what my run is. My run can be infinity because that line can go on forever. I don't really care because whatever I do with 0 divided by anything is always 0. Then we move on to the vertical lines, and vertical lines are also equally as awesome because, yes, what's the gradient? Well, again, if we use gradient is equal to rise over run, then what do we know? Well, the rise can be infinity. I don't really care what it is. Let's call it infinity. But my run, how far across does that move? Well, it doesn't. It doesn't have any horizontal distance. So the run there is 0, and anything divided by 0 is in fact infinity, or as your calculator will say, undefined. So knowing that that is 0 and that is undefined is incredibly important. And as I said slightly earlier, I'm going back over this again, knowing the fact that this has a gradient of 0 and this has a gradient of 0 allows us to use differentiation or other maths coming up later on to help us find those coordinates of what we call the maximum and minimum. If you don't understand what you're finding with a gradient, then unfortunately differentiation becomes difficult, because while the maths behind differentiation isn't hard, I promise you, it's so simple. And I think I did a bit of it in the last video. What I can tell you is unless you understand what you're doing as in terms of finding gradients I think it all just becomes a bit of a fog. So let's have a look at now the relationship between the gradient and the angle. Now, as I said earlier, there is my x-axis, for example, and there is my positive gradient. And between the two, there will be an angle. Now, in fact, that angle is true anywhere along that line. So there is theta, there is theta, there is theta. So what we need to do is find a way of expressing sort of with words what we're trying to find. And what we do is we say, find the angle between the positive direction of the x-axis, so it has to be the positive direction of the x-axis, and the line. Why would we need to do this? Who knows? Why do we need to do anything in maths? Remember, we're just doing this to get us to the next stage. It has no real practical applications. Lol. And maths teachers around the world are going, shut up, what are you doing? So, as I said right at the beginning of the video, we've already had Pythagoras theorem and trigonometry taught to you. So here we go. There is my rise over run. From my previous question, what did we have? We had my rise was 3 and my run was 4. Is that true there? Yes, it is. So using those two examples, we've got a rise of 3 and a run of 4. So we know that my gradient, which is equal to rise over run, becomes equal to 3 on 4. Yay, life goes great, and that had nothing to do with Pythagoras theorem. Now I'm going to put a theta in here. And has your brain now jumped to to trigonometry? Well, hopefully it has, because when you put a theta in there, you look at the sides, don't you? You say, oh, okay, hold on a moment, that's called the opposite. And that's called the adjacent. And I now can find that angle using a trig ratio. So I now know, hopefully, that tan theta, which is the opposite over the adjacent, is equal to 3/4. Hold on a moment. 3/4 and 3/4. That cannot be a coincidence, and as it turns out, it isn't. Because in fact, we know that if the gradient is equal to the rise over run, and we know we can write the rise as otherwise known as opposite, and the run is otherwise known as adjacent, which we just so happen to know stands for tan theta, then we can cut out the middlemen and have that our gradient is equal to tan theta. OMG, this stuff is freaking awesome. So what it basically says, if I know the gradient of a line, I can find the angle between that line and, in this situation, the positive direction of the x-axis. Okay, so how am I going to use that information to then find my angle? Well, I know that m equals tan theta. Scrolling up a little bit, I therefore know that tan of theta is equal to 3/4, and so theta must be tan to the -1 of 3/4. Put that in brackets to make it nicer. And just load up my calculator. So there's my calculator. CAS, this is the Casio ClassPad, or Casio ClassPad, he said, easy for me to say. And I'm just going to hit main, I'm going to hit keyboard to bring up my trig function. And then I'm just going to go tan to the -1 of, what did I say, 3 divided by 4 equals, and out comes 36.86 degrees. So theta is 36.86 degrees, and that's this angle here. So this angle here, and this angle here, and this angle here. One thing to notice about your CAS calculator as I bring it back up is to make sure that your angles is in degrees for questions that ask for degrees. Later on we deal with radians, and then most of your questions will be in radians, and it's always vitally important to know to make sure that you've got your calculator in the right mode. That was finding the angle between the positive direction of the x-axis and the line, but that was a positive gradient. What happens if we have a negative gradient? Well, if we draw a quick sketch, and here is my negative gradient, first things first is try to identify which angle it is talking about. And because you want it between the line and the positive direction of the x-axis, it's actually that angle there. Okay, that's interesting. So what are we going to do here? Well, let's have this coordinate point here as 0, 3, and let's choose a coordinate position here of 2, 2, for example. Right, so we've got 2 points on that line. Can I find my gradient of that? Because at the moment we know that m is equal to tan theta. Okay, we know that m is equal to tan theta, but that was, in this situation, for a positive gradient. This is a negative gradient. Let's see what actually happens in this situation here. So we know that our gradient is given by y2 minus y1 over x2 minus x1. So we're going to call that x1 and y1, and we'll call this x2 and y2. Right, okay, thank you very much, ladies and gentlemen. What are we trying to find? Well, so y2 is going to be 2 minus y1, which is 3, over x2, which is 2, minus x1, which is 0. So it gives me y minus 1 on 2, so my gradient is negative a half. Now in this situation here, that negative sign basically means I've got a negative gradient. We know that. We can see that on my diagram. But to be able to find alpha, all I want to do is opposite over adjacent. Yes? So when I want to find alpha, I just need to do the tan or the inverse tan of the opposite over the adjacent. So the negative sign is completely irrelevant. I just want to find the inverse tan of a half. So I now know that alpha is equal to the inverse tan of a half. That minus sign doesn't tell me anything. I'm looking for opposite over adjacent. I don't care about the minus sign. So when I put that into my calculator, loading up my calculator, then what you see, because I've already just done this calculator, is that the angle alpha is 26.56. So we now know that alpha is equal to 26.56 degrees. Is that my final answer? No, because it's not alpha we're trying to find. Remember, it's between the line and the positive direction of the x-axis, which is this angle here. And so how do I find that? Well, if I know alpha, I'm going to take it away from 180 degrees. So loading up my calculator, 180 minus answer equals 153.4 degrees. So alpha, so theta is 153.43 degrees. Now, I always do things to 2 decimal places. Why? Well, because that's what I was taught at school. But in methods, you always have to write answers to exact values unless otherwise stated. And so probably for this question, if it had been in an exam, they would have said, write your answer to the nearest whole number or to 2 decimal places. Please, please, please read the question. All right, ladies and gentlemen, that is it for this lesson. Thank you very much for watching. It's the gradient of a straight line. We did a little bit more than just the basics of rise over run. We looked at sort of differentiation and how we're going to use it for curves. We looked at the idea of relating it between a line and the positive direction of the x-axis, and I am done. Thank you very much for watching. It's really good to see you. If you can, do me a favor and subscribe. Otherwise, I will look forward to seeing you the next time. There's a video loading over there for much more math fun with relation to this course. And yeah, have a really good day. All right, MaffsGuru out. Bye-bye.